Hello, everybody. We are David Owusu and Rodrigo Ledesma, and we will be talking about an article called The Complexity of One Machine Batching Problems. So let's start by defining what a batch is. And the objective will be to have a sequence of jobs called JS, and we need to find partitions of HS into batches with an optimal value. Here we will be having n different jobs from 1 to n, and also each job will be linked, will have a processing time. As you can see, each job has one processing time associated with it. So we have both n jobs and n processing times. The other important concept will be the batch size, which in this case is going to be given by a number of jobs that are inside one batch. It is important also to state that for each batch, we need an amount S of time that is just the machine setup. In order to obtain the optimal value of the size of the batches, we need to use an objective function, which is the sum of all the weights of each job and also the flow time of a specific set of jobs. That is going to be the time where the batch finishes. Now let's give an example. In this case, here are our processing times, and this is the example of how they are going to be scheduled. In this case, our weights are 3 because we have 3 jobs here. The flow time is 5 because the first one finishes at 5, and that subsequently the objective will be to minimize this sum, this 53. The interesting part of this paper is that based on the characteristics of the problem, it might be polynomially solvable or NP-hard. If we're solving only the flow times, this can be solved in polynomial time. But when we add the weights, that stops being polynomial and becomes NP-hard. So we will be seeing some of these examples. This paper is divided into 2 sections: the algorithms that can be solved polynomially and those who are NP. In this case, we will start by the ones that are solved polynomially via a reduction to the shortest path algorithm. This is how we are going to be representing the reduction to a shortest path. We'll be introducing the concept of the cost from going to one job or set of jobs to another. And well, this is like a more graphical representation. And as we have seen in class, we will be using the shortest path algorithm, which comes from dynamic programming. Here, let's introduce first some concepts, starting from fj, which is just the shortest path from j to the end. And also we have, for example, fj of k, and in this case it would be also the shortest path, but starting in the node jk, or in the edge jk. To find the shortest path, we need to find the minimum between either the shortest path containing the node jk or the shortest path which doesn't contain it. We need to first understand 2 lemmas. The first one just states that if we pass a threshold, then it is better to use the vertex k than the vertex L as the next step. The second one compares 2 thresholds, and based on this, it also states which one is better to use or not to use. Now, our algorithm is going to be supported by 2 different helping arrays: Q, that will be used to help calculate the optimal values, and N, when the optimal values are going to be stored. We're going also to be analyzing all the nodes from the biggest, from the farthest to the right, to the first one, starting by initializing our Q with n plus 1. If n equals 6, then Q has a 7. In our first iteration, J equals 6. So Q has the 7th vertex, and in this case, we're going to be analyzing this condition. It's not going to be true because it's the same. So we don't delete, we don't enter, we just store the 7th in our n. Now we will be adding j equals 6 to q, as we have seen here. Now the head and the tails are different, so this condition is complete. We now go to evaluate the threshold limit. In this case, this threshold equals this, it's just an example. And f of j, which is the sum of the weights, in this case equals 2, so it's bigger. We enter, we delete the head of q. In this case, the head of q is 7, and q has now only the 6th. And we put in the 5th position the number 6. Now our optimal path has this vertex. Let's say that we're in an iteration x, and let's see what is happening. So we will be comparing the head, the tail, and the first lemma. Whether one is incomplete, we will not enter, we will not any deletions. We need both to be complete to delete the head of q, like this, until we have only one element. And that element is the one that is going to be giving us the next step towards our optimal function. What we're doing here is we're also analyzing which is the optimal size of the batch. For example, here it might also be the first one, or our batch size can be 2, containing 2 different nodes, or it could be 3. This is what our conditions are evaluating. At the end of the day, our algorithm is going to give us the shortest path, and also it is going to give us the optimal batch size.
So for this particular problem, there's an arbitrary number of jobs, and the jobs are all independent, meaning they can be scheduled in any order. The objective function is given in point 3, and we are going to provide a proof of NP hardness by reducing it from an instance of the 3-partition problem, which in itself is NP hard. So our problem P has a solution BS if and only if the 3-partition problem has a solution as well. So the paper gives us some properties the optimal solution of this problem would have. So an optimal solution would have this number of jobs, and for the optimal solution, the sum of the weights for every batch should be equal to the sum of the processing times. In reducing an instance of the 3-partition problem into an instance of our problem, we follow these steps. First, for every integer of the 3-partition problem, we are going to define a corresponding partition job, and where the processing time for that job is going to be equal to the weight, which will be equal to the integer value. Next, we are going to define our dummy jobs, and for each batch, we are going to define a dummy job with this processing time, and the processing time is going to be equal to the weight as well. Next, we create one final dummy job j for n plus I with processing time 2b and weight also equal to 2b. And then we set the setup time to s is equal to 2b, and then our threshold value is given by the equation in number 5. So the dummy jobs are very important in that they serve as a sort of padding that allow us to reduce our 3-partition problem into an instance of our 1-machine batching problem while still satisfying all the constraints of a 3-partition problem. Now, our problem P would have a solution BS if and only if the 3-partition problem also has a solution. So the paper goes on to give us some properties of the optimal solution. So the paper goes on to propose a lemma that they prove by contradiction, and based on that lemma, the unique optimal solution BSK would have m plus 1 batches, and the batch sizes are given by the equation also shown below. So if we look here, we'll see how the structure of an optimal solution BS for the problem is going to look like. So in summary, we have shown how a 3-partition problem can be reduced into an instance of a 1-machine batching problem, and we've looked at some of the properties an optimal solution of the problem will have, such as the number of jobs and the batch sizes, as well as the relationships between the processing time and the weights. Now, we've also shown that this solution can only be achieved if a 3-partition has a solution. That is, if and only if the sets of the subsets that the 1-batching problem will be reduced to can be scheduled such that for each batch the sum of its elements will give us B.
So now we are going to offer a numerical example for the problem P to make it all more physically understandable. So first, we are going to create n jobs, one for each AI. Then for each job, GI will have processing times and weights equal to 2. And then we are going to use all the equations that were provided in the previous slides to verify whether this solution would hold for both the 3 partition and the 1 machine batching problem. So we create dummy jobs as well and set them to the required values per the instructions of the paper. So after creating all the required variables and dummy jobs, we can see that the transformation can be done in polynomial time, and thus our process is correct. Now the important step would be to show that the equations and the inequalities that were provided as proofs in the paper can be satisfied by our example. So for each of the jobs, we are going to ensure that the batch sizes are going to be 2 plus m minus j times 2b. So we do this for each of the jobs that we created and we observe the results. So finally, we check for each job whether they satisfy the inequalities that were provided by the paper. And for each of them, we see that this is true. So our experiment has turned out to be true, and we can conclude that the 3 partition problem indeed has a solution. And that solution by polynomial reduction is correct to provide an optimal solution for our 1 machine batching problem.
So the precedence constraints for this particular problem would result in parallel chains. A chain is simply a form of graph where each node has at most one predecessor and one successor. Okay, so the properties of this problem are shown below. The precedence constraints form parallel chains. All the jobs have the same processing time. The problem is in the class NP, and the objective function is also given below. So we are going to prove NP hardness by offering a reduction from the very first NP hard problem that we proved in this paper. So given an instance P of the first problem we covered in this presentation, we are going to reduce that into an instance of our chains problem. So first we say let n be the number of jobs in an instance of our first problem P. For each job Ji, we are with a processing time Pi, we are going to construct a chain with Pi jobs. So each of these jobs in this chain we are going to call chain jobs. All the chain jobs will have a processing time of 1, and the first Pi minus 1 jobs will have a weight of 0, and the last job in the chain will have a weight of Ai. So this problem is very similar to the problem we just saw. The only difference is that for this problem, the jobs have arbitrary processing times. So it's also in the class NP. It has the same objective function. And for this one, we are going to show its NP hard by presenting a reduction from the partition problem, which is another well-known NP hard problem. So for the partition problem, given a set of positive integers, our goal is to split that set of positive integers into subsets such that the sum of all the elements of the subsets are equal for all the subsets. So in reducing from the partition problem to an instance of our modified chain problem, first of all, we define Rb, which is half the sum of the first m positive integers. Then we are going to construct a chain Ci consisting of Ai jobs. The first job in the chain is going to have a processing time of Ai plus 1, followed by all the other jobs having a processing time of 1. So we can see what the structure of the chain job is going to look like in the diagram. Then we are going to define dummy jobs Ji with processing time of 1 for the first B elements. Then we are going to set the setup time to be S is equal to 2B and set the threshold value to be 19B squared. An important point to note is that an optimal solution for this particular problem is going to have 2 batches or 2 chains in total, and this was proved by contradiction in the paper. So first of all, we schedule all the dummy jobs into the first batch, followed by a subset T of jobs. After that, the remaining jobs are scheduled together in the second chain, and any alteration in this particular structure is going to result in a loss of optimality of the function.